Today I'm going to be talking about some MLCAD algorithms. So first of all, I wanted to start off by saying, do you know how many placement runs we start in SoC physical design? In Qualcomm, we start one placement run every 30 seconds. Whether it be for floor plan exploration, for PPA exploration, for other validation runs, design validation. So that's what I wanted you guys to just look at this scale. So before we get into the details of this, I just wanted to go. So Qualcomm has been in the forefront of the mobile SoC integration. We integrate GPUs, call it Reno. We integrate the cameras called Spectra. These are internal names, external names as well. We integrate AI, box, and of course we integrate the modem. So integrating all of these onto the single die with the power, performance, and cost, I think form factor, I think we talked about just now, all of these into that single die is not a small feat. And we have been doing that since a long time. And you have seen these devices in all the latest Android smartphones. So everybody knows Qualcomm has been a leader in mobile, but we also have devices on the other areas, including the automotive, compute, AR, VR, and wearables, and earbuds, as low as earbuds in the voice and music. So we have one technology roadmap, which we have all these IPs, the IPs, the GPUs, CPUs, and we try to design for scale for as small as earbuds and as big as for data service and compute. So making sure the PPA is met at every single design space. So we have been, as you guys have seen over the generations, these are the various generations from a long time. All the Snapdragon generations, premium tier Snapdragon generations. We have been getting, based on the design and other techniques, we have been getting performance gains in the CPUs, GPUs, AIs. So as we go now, and the Moore's law not scaling, we are not able to get these gains from the technology. So we need, for design techniques, and we need CAD techniques to get this performance gains in order to maintain the leadership. So the PPA in these design spaces, such as the wearables, the glasses, the handheld gaming, and the virtual reality, these offer different constraints. In addition to the area and the power, these also have thermal constraints like people talked about. So we need to make sure we are marrying all these constraints and designing. So all these constraints now come into the forefront. I just wanted to just dive a little bit deeper into it. This is the graph showing on the x-axis is the die size, and the y-axis is the die cost. And if you normalized, and the three lines on this are the various technologies, n-1, n, and n. As you know that this having an extra performance and features does need to increase the die size. If you look at the same die size in two technologies, the cost itself is about 80% larger. You can look at these 2 points. So the same generation, next generation, you even keep it, you do your PPA and keep it to the same die size, you still are paying for the cost. So the cost is very critical. So because of the next technology, the wafer cost is high and the yields are lower. So obviously all of this adds to the cost. So we need to work on the PPA. So this is another view of the growing complexity for us. As you're seeing that everybody wants the faster GPU, much performance on the camera. So integrating all of this and having all these extra features has been throwing our transistor count over the last 5 generations, see it's almost a 4-fold increase in the transistor count. So we now have a need to limit the power and minimize the die area to corral this one. So we need the PD tools and the ML to help in this regard. So this is just going a little bit deeper into the thing. Qualcomm designs, the large designs, are very hierarchical in nature, divided into multiple hard macros and subsystems. And we call a hard macro, which is a standard cell plus memories plus some analog blocks. We call it one hard macro. These on the top right are shown the different hard macros. These are the runtimes. I mean, I purposefully left the amount of time, but the runtimes of each of these macros is exploding, more than 2+ weeks. I mean, some of the larger hard macros. So and if you look at the number of runs we are able to do with that increased runtimes, it is starting to reduce the number of runs we can do in a given schedule. So our number of runs are limiting the amount of PPA that we can gain in these. And the transistor count explosion is leading to larger runtimes, and now larger runtimes are leading to less number of runs, are affecting the PPA. So we do need a solution for this. So in addition to runtime, I think we've talked about before, companies like Qualcomm should have unlimited compute and storage, but that's not the case. So all of these runtimes, what I've done is increased our compute requirement about 3-fold. So to deliver these performances, we do exploding compute. So in order to tackle all these problems, we have proposed a physical design process, an ML-based process. We know that the final place and route needs the EDA tools. But what we wanted to, our approach for ML has been to use ML to augment the EDA process. So we wanted to have some good predictions for whether it be placement or whether it be any other step in our design flow. So in the next few minutes, we're going to talk about a couple of examples on the placement and the STA. So this is what we call, we projected, we did this in one of our projects. This is a very small example. This is showing the placement of a small macro, a hard macro, where it shows the module placement of various blocks. If you look at the module placement on the top, it shows the modules, standard cells are placed in a long, elongated way, which was reducing our PPA. So with the human intervention, now, once the designer was able to see the placement on the left, he was able to immediately move the memories to the right and be able to put the modules in the proper way to achieve it. So this is where we achieved a 2.3% better wire length. But the beauty about this is we did not take the runtime of the entire EDA placement time, which is what we have talked about. The placement times have increased, the PNR times have increased. This can get in much faster than what it is. This is a small example, but bigger examples are there, and we have seen better. So we are using ML to provide the information back to the designer in a very quick fashion, so that we don't need to do as many placement runs that we talked about in the beginning of the talk, or we can reduce the number of placement runs. So that's about how to aid the placement or part of the thing. So the next thing is the starting type STA. Usually in our physical design process, we have a floor plan phase and a dry run phase and a final run phase. And during our final run phase, I mean, each of these is about 2 months, sometimes 4 months. But the last 6 to 8 weeks, or about 2 months, is all timing closure, and obviously physical verification, and then tape out. So, and based on our operating voltages and the what do you call it, the deep submicron technologies, the number of corners has exploded. So I don't want to name the exact number of corners, but there's safe to say more than double digits, right? So when you want to run so many corners or STA for these entire chips, the compute just explodes. The number of ECOs required to do it takes longer. If you want to run all the corners, it takes longer, because even though every corner says that we run it in like 15 hours, 20 hours. But the problem is that when you have a STA run, by the time you run all the corners, it takes about a day and a half, 2 days. So that just elongates the ECO cycle. So what this technique was trying to do is try to run STA in a small subset of corners and predict the slack for the full set of target corners. ML has seen these kind of problems in the sparse problems in the multi-view services and the B-spline approximation. So let's go a little bit detailed into what we do in this list. So we take the STA runs, and we look at, we take each corner and we use an ML to predict the slack in that corner based on the slacks of all the other corners. And using that, you create this ranked matrix. Then you know that which corners are useful for predicting the slack, and which are, so by that you predict the number of corners, you get the list of corners, and then you run those corners as deep into your timing closure process as possible. So you're running on a smaller subset of corners. So and once you run on the smaller subset, you use the neural network to predict slack in the other corners, and you fix with that. So you basically are now running a less number, compute is low, and your runs are coming faster. You do lesser number of timing ECOs in a lesser amount of time. So what we have seen is that it enables faster timing closure. This is over the last few generations. We have seen at least 7% reduction. We have increased from 3% to 5% to 7% over the last week. It's an improvement of our process and models and how we are modeling. So I just wanted to say that, like, on our current design process, we have we just added a few bullets here, but it goes from floor planning, synthesis, place and route, and various sign-offs, including DRC closure. So we are trying to address challenges in each of these steps. And we are trying to augment ML for all of these steps, including, so our challenges are in macro placement, our challenges are in place and route, our challenges are in, we're looking at challenges in DRC closure, IR drop prediction. A lot of these, these are the challenges that we are trying to address. So in concluding my talk, so until now, all of our ML has been looking at prediction, meaning in the sense, like in the placement, we say, how do you predict placement? And looking at, okay, if you predict placement, based on that, you're making your final lesser number of placement runs. And you predict timing closure, you're making lesser number of STA runs. You're predicting either DRCs or predicting IR drop. So but now you have to go from prediction to optimization in that. So I think that is the next steps that we need, and we need the community. And we also are looking at various other, keeping the human in the loop, in terms of, like, for example, sometimes the designer's intuition saves a lot of effort. So we need to figure out how to get that into it. And it can run for some time, but maybe some designer intervention requires, and so that it will be better. So what we're using ML for is to increase the productivity by able to reduce less number of EDA runs and get better PPA in terms of both area and power and obviously performance. And we also want to reduce the amount of compute we use, so using ML. So we need to all innovate together to improve this ML. So what I'm requesting the community here is, I think a lot of the problems are working on something 3 to 5 years down the road. But we need solutions for the next year. So we need that incremental help as well. So because we can't wait 5 years to get that problem. So I think it is good to work on both moonshot problems and also the problems which can help in the near future. So I request the community to work on those two things. Thank you.
Questions, please.
Thanks. Could you show the results slide for the timing analysis?
Yes, 1 second. Sorry.